So let's go through some more examples. I wrote this one down last time, so find the interval of convergence for this. So hopefully you work that out. You let U be this series, right? Then you apply the ratio test. So here's the ratio test. And you get down to opposite value of x minus 3 less than 1. And so if that's the case, then you have convergence, right? That's what we get. If you have, and then to solve the x minus 3 less than 1, you're doing the, you do -1 less than x minus 3 less than 1, and then you solve, right? You add 3 everywhere. So you get your endpoints of 2 and 4. And so if x is less than 2 or greater than 4, the series diverges. So then we go on to test endpoints. And you're substituting into u. So you're putting it right here. And you get a 2 minus 3. So right, here's your 2. So then that alternates, but that's just, you add those up, that's just n plus n, which is 2n. Well, 2n is always positive, so that's just 1 over n plus 1. Well, that's basically a harmonic series. So if you start at 0, it's the same as starting at 1, and you get the harmonic series, which is divergent. So at 2, it diverges. Okay, then for x equals 4, you put in 4, subtract, and you get a net. You get a positive 1. So this is just 1; it's gone. So this is alternating. If you rewrite it in this form, it looks a little better. You get an alternating series, and then that's convergent by the alternating series test. So at 4, it is convergent. So the interval of convergence is 2 to 4, not including 2, including 4. Okay, so work through that if you hadn't already worked through that. So next is differentiation integration of power series and kind of some power series representations. So here's our power series. And you assume F has a radius of convergence of R, whatever that may be. Okay, so F it's the claim, and then there's no proof to this, but it's not too bad probably. F is continuous and differentiable and integrable. And furthermore, you get what it is. F prime is this, and the antiderivative F integral of F is this. You get an arbitrary constant, of course. They put this in front just to not confuse it with terms over here. Okay. The radius of convergence is equal for f prime, and the integral of f. But the endpoints you have to test. All right, so try this example here for power series. So find a power series representation for ln. ln1 plus x. If x is less than 1. All right, there's a bit to do here. So just note that this can be expanded. And so I want you to try to work out these step by step and see what you get. Okay, so this is one way to show what a function is. So this function is equal to this, and will converge to the natural log, but that's only true for values less than 1. So like you can test, you can do natural log of like 1 plus 0.5 or 1 plus negative 0.8. So it has to be within that interval, and then you can test, or you can extend terms of the sequence and figure out that what its approximation is. So these type of things were very valuable before computers. That's all this stuff was done well before computers or anything, no idea of computers. So this convergence concept is allowing us to calculate this to many decimal places. And sometimes the faster this converges, the fewer calculations someone would have to do. So very powerful stuff that they're using here.